Hi guys, welcome to another stats video. I hope you guys are having a great Saturday. This is going up a little bit later than I originally intended. My apologies for that. Thankfully there's only one model here and we're going to get plenty of practice with it on Monday in groups more than with me covering more stuff at the board for you guys. Alright, so we're going to talk about two things here, and those are in the title. Binomial model, which is like a more interesting version of the geometric model that works with Bernoulli trials. Again, Bernoulli trials, remember, have success or failure, and Bernoulli trials are always successive trials that are independent. So the success or failure of one trial does not affect the success or failure of a subsequent trial. And then the normal approximation to the binomial model is a really, really good shortcut for using the binomial when numbers get large. And that'll make more sense in just a second. Okay, first two slides that we've got here are really building up to the binomial model. In the binomial model, there's this combination equation which is tricky to understand unless you've seen it worked within an easy to understand context. So I'm going to try to present to you guys this easy to understand context here. Alright, so in how many different ways can I choose 5 hats from a collection of 5 hats? Where the order in which I choose the hats does matter. And everything in parentheses, don't worry about making sense of that just yet. That'll make sense a little bit more next slide. Well, okay, let's let capital A, somewhat randomly here, represent one of our hats. So let's think of this in terms of us having 5 buckets. If I have 5 hats to choose from, and I'm filling those buckets in a particular order, I could have, if I have, first case here, 1, 2, 3, 4, 5 buckets, I could say, well, okay, we could choose for the first bucket, I could first choose of the 5 hats, the first hat, A sub 1, then I could choose A sub 2, then I could choose A sub 3, then I could choose A sub 4, and then I could choose the 5th hat, A sub 5. That's one possibility for choosing these 5 different hats. Another possibility, and if you see how this is going to work, don't worry, I'm not going to show you 120 different combinations of this. You could also separately say, okay, well, we choose the first hat, A sub 1, then instead of the second, we choose the third hat, then we'll choose the second hat, then the 4th and the 5th. Hopefully that makes sense so far. So that's what the question is getting at. How many different ways can I select hats if I've got 5 to choose from? Well, let's go ahead and skip down here and get to the heart of the matter. There are, in my first bucket, let's put G instead of a number here. We're generalizing here. The first bucket can be filled 5 different ways, right? And then the next bucket can be filled 4 different ways. The next after that, 3. The next after that, 2. And the next after that, 1. Because I'm not giving myself the opportunity to choose a hat and then choose that hat again. Once I've chosen it to fill a bucket, so to speak, once I've chosen it in a particular order, I can't choose that hat again. Well, this 5, 4, 3, 2, 1 thing, these separate trials, we could actually represent with a probability tree. That would be huge and complex. But there are 5 times 4 times 3 times 2 times 1, which equals 120 different ways that I could choose these 5 hats. Now, instead of 120, I actually want to write this. 5 times 4 times 3 times 2 times 1 is actually, we've got a shorthand for that. As scientific notation is to standard notation, the factorial is 2 products of subsequently smaller numbers. 5 factorial is equal to 120. So let me show you just another factorial here too before we go on. Another factorial. Let's say we've got in green, because this is just kind of an aside, if we were talking about 3 factorial, that would be the product, 3 times 2 times 1. If we're talking about 7 factorial, that is 7 times 6 times 5, that's 4 times 3 times 2 times 1. And by definition, if you're wondering what 1 factorial is, that's just 1. 0 factorial is by definition also 1. And that's for reasons of division, but that doesn't really matter. That's, again, an aside. Okay, so there we go. We found how many different ways you could choose 5 hats if the order in which you chose those hats matters. Okay, now let's build on that a little bit. In how many ways can I choose 2 hats from a collection of 5 hats, where the order in which I choose the hats does not matter? So 2 different things going on here. First thing, we're only choosing 2. Second thing, the order in which I choose the hats doesn't matter. I.e., if I choose the first hat, then the second hat in that order, we're going to count that as being the same choice of hats as if I chose the second hat, then the first hat. So, let's see. I have, to attack this problem, I'm first going to look at this piece right here, 2 hats from a collection of 5. Well, you can see all these pairings where I've represented for you the different possibilities where we're choosing these hats to fill these buckets. The buckets aren't being underlined like they last slide, but it should still make sense. All these are different pairings in which we can choose these 2 hats of 5. So there are, in all, 5 times 4 different ways in which I can choose these hats. I have 5 selections for the first bucket, multiplied by 4 remaining selections for the second bucket. Right? Well, 5 times 4, I can actually represent, that is, I can say that that is 5 factorial over 3 factorial. I'm going to represent this multiplying using the factorial shorthand. Why does that make sense? Well, 5 factorial is 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. So they are indeed the same. 5 times 4 is the same as 5 factorial over 3 factorial. That, as I'm sure you know, that's equal to 20. So there are 20 different ways in which I can choose 2 hats if the order did matter. Well, okay, but they wanted us to come up with the number of ways I can choose these hats where the order does not matter. Notice that, let's erase these blue arrows so that we don't get visually overwhelmed here. If I'm looking at this unique combination of hat selection, the first and then the second, that should not be counted separately of this guy right here, because I'm choosing the same 2 hats, and they said that they didn't want us to choose these hats in such a way that the order was important. So these guys really count as the same selection, even though the order I chose them in was different. Same thing with, for instance, this guy and this guy. Notice, you could go through the table and verify this, for every unique selection of hats, the first and the second, there are duplicates. You have 2 versions of that same unique selection of first and second. You have 2 versions of that same unique selection of first and fourth, right? So what do we do with those? Well, we divide them out. We don't truly have 20 different unique hat selections where order doesn't matter. We have 5 factorial over 3 factorial divided by 2 factorial. That is to say, 5 times 4 times 3 times 2 times 1 over 2 factorial is 2 times 1 times these 2 guys right here are just multiplying because they're adjacent. Times 3 times 2 times 1. So we have, let's break this down. This piece right here that I am, let's first cross out things that are alike, the 3, 2, and 1 there. This piece right here that I'm circling in green, that tells us the number of different ways that of the 5 hats, I can choose 2 of them. 5 times 4 different ways. Now, that's the first thing that we've already talked about. The 2 times 1 cuts out, it divides out those ways in which my selections are identical, even though the ordering was different. Because we want to divide them out again because the order does not matter. So, how many different ways can I uniquely choose 2 hats of 5 in all? Well, that's 5 times 4 over 2 times 1, which is equal to 20 over 2, which is 10. There are 10 different ways that I can uniquely choose 2 different hats of the 5. Okay, that leads us to the combination equation. Okay, this is the big thing we're trying to build up to for the binomial model. The combination equation is as follows. Let's do this in, I know I jump around with my color coding. Let's do this in black. Combination equation big idea, you better believe this is going to be on a video quiz if we have time Monday to look at that. That is as follows. N choose K. So if I have, for instance, 5 hats that would be my N, and I choose K of them, or 2 of them in this case, that's equal to N factorial over K factorial times N minus K factorial. Okay, now let me go with an aside here real quick. I want to make sure that this is well understood in an example before we go on to the next slide and start to use the binomial model. Let's talk about the number of ways I could choose 3 students from the class of now 29 of you. So if I have, in this case, we're saying 29 students in all, choosing 3 of you, so N is equal to 29, K is equal to 3. So the combination equation would say, okay, well, there are 29, choose 3 ways to do that, which is 29 factorial over K factorial first, 3 factorial. Again, this guy right here divides out the number of different ways I can choose if order did matter, but we don't care about that. If I choose Chandler, then Quinn, then Brooke, we're going to consider that to be the same result as me choosing Brooke, then Quinn, then Chandler. It doesn't really matter. I got the same 3 students. So that's 29 factorial over 3 factorial. That looks messy. Let's clean that up. 29 factorial over 3 factorial times N minus K factorial would be 26 factorial. Right, like that. So I don't have an answer for this that I've pre-computed, but that would be 29 times 28 times 27 times 26 times dot 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 number of ways over 3 times 2 times 1 times 26 times dot dot dot. And again, these guys cancel. So you have 29 times 28 times 27 over 6 different ways that we could choose 3 students from this class of 29. That's what the combination equation does for you. So I think it's kind of cool, it's kind of powerful. I feel like there's a lot of applicability that you could find in the real world for this combination equation. This was one of the biggest things that I left a discrete math class with in college, thinking like, oh, okay, that's cool, I can use that. So hopefully you feel the same way. All right, now let's finally use the binomial model. Yeah. A wildlife biologist examines frogs for a genetic trait he suspects may be linked to sensitivity to industrial toxins in the environment. Previous research had established that this trait is usually found in one of every 8 frogs. He collects and examines a dozen frogs. If the frequency of the trait has not changed, what's the probability he finds the trait in first 3 or 4 frogs? Okay, so part A, let's see here. We are going to start by defining a random variable. The random variable that we care about, let's just call that x, partly because I like to draw the x with the little bars on it. I think it looks cool. It's equal to the number of frogs found with the genetic trait that this geneticist cares about. Wait, genetic trait. There you go. And we do have Bernoulli trials here. Notice each of these frogs either will or will not have the trait. And if I choose one frog, that will not affect whether or not the next frog has that trait. So these are independent trials. So the probability of success, the probability that I find I almost said a dog with this trait, a frog with this trait, is 1/8 or 0.125. Obviously then Q, the probability of failure, is 7/8 or 0.875. Okay, so we care to find that the probability is of X, the number of frogs found with this genetic trait, is either equal to 3 or that it's equal to 4. Okay, now just because I use this union symbol right here doesn't automatically mean that I have disjoint events in capital X equaling 3 or capital X equaling 4. But let's think it through. Is that the case? If I've got a dozen frogs that I'm selecting from the froggy environment, and I'm checking to see if 3 had the genetic trait or 4 had the genetic trait of the dozen. Those truly are disjoint events. I can't have 3 and 4. Only 3 and only 4 have this genetic trait at the same time. So we can break this apart as the probability that capital X is equal to 3 plus the probability that capital X is equal to quattro. So, okay, now how do we find those? Well, we're going to break it up and consider this to be 2 different things here per probability that we're finding. So, what do I mean by that? I mean that the probability that the number of frogs of the dozen that we find have, we have 3 of them with a genetic trait. We're going to multiply 2 things here. The first thing that we need is the number of different ways, and actually I'm going to write the first thing in the second blank. Let's think of it this way. What's the probability that I find 3 frogs with this trait if there are a dozen of them? That I have just one of these outcomes where there are 3 frogs of the dozen with this trait. Well, that would mean that we had 9 failures. 9 frogs did not have this trait, times 3 frogs we did find with a success with this genetic trait. So that's the probability that I would find 3 successes of the dozen one time. But think back to the hats. There are lots of ways that you can have 3 frogs of the dozen have a success with this genetic trait, have this genetic trait. I could have the first, second, and third frog have this genetic trait. I could have the first, second, and fourth. I could have the first, second, and fifth, etc., etc. Those are all unique combinations. So in the first blank, we have to multiply by the number of ways that this can happen. That is to say, of the 12 frogs, we're considering us to have chosen 3 of them with this success, 3 of them with this trait. So those 2 things multiplied together is the probability that the number of frogs found with this genetic trait is equal to 3. Excuse me. So we're going to add to that, because we've got disjoint events. Again, 2 things here of another product. We have, again, second blank first. Well, if we had 4 successes of the 12 frogs, that would mean 8 failures times the 4 successes. But that doesn't take into account all the ways in which you can have 4 of these frogs successfully have the genetic trait. Well, that is just, again, the combination equation here. 12 frogs, and we're choosing 4 of them. So what does that look like? This is messy. An FYI here for you before we start to do a whole lot more calculation stuff. The binomial model, which you're just about to see, does have a really, really good calculator shortcut. I will show that to you next time I see you in class, and it'll save you a bunch of time. So don't worry too much about the mechanics of the calculations. Try instead to focus on understanding what the problem's doing and where the math is coming from. That's more what I care that you understand. Okay, so what does this look like? This looks like 12 choose 3 we know is 12 factorial over, remember, n choose k was the generalized form of the combination equation. So 12 factorial over 3 factorial times n minus k factorial is 9 factorial. Whoops, what is that? A semicolon? No, we want an exclamation mark for factorial. Okay, so we've got that. We've got the number of ways that we could have 3 successes times 0.875 to the 9th times 0.125 to the 3rd plus 12 choose 4. You guys know, well, I don't really need parentheses there. Let's do this. 12 factorial over 4 factorial times 8 factorial, all multiplied by 0.875 to the 8th, the number of failures we have of these 12 frogs, times 0.125 to the 4th, the number of successes we have of these 12 frogs. Not too bad. Okay, so I'm not going to draw that out further. That's as much as you're going to get from me in terms of the guts of working with the binomial model. This first thing here comes out to be a probability 0.1292. The second thing right here, this nasty product, is 0.04153. In all, the probability that we would have 3 or 4 frogs with this trait is 0.17073. And there we go. All right, so I've kind of used the binomial model, but I haven't really introduced it generally. So I guess because I don't seem to ever have a color coding scheme, let's go with what I've used this slide so far. So black's going to be our general formulas that we're talking about with the binomial model. Again, that works with Bernoulli trials that have to be independent. So success or failure, one trial doesn't affect the next trial's result. If n is equal to the number of trials, that would be 12 here for the example above. If p is equal to the probability of success, that I'm sure you guys all know, but I wanted to put it for the sake of clarity anyway. And x, capital X, is equal to the number of successes in trials, then this that follows is the generalized binomial model. It is the probability that my random variable x equals some specific value. Could be, for this case, 3 or 4 like we just saw. It could be something bigger, could be something smaller. That is equal to the number of ways I can choose of my n objects to have x of them have successes times the probability that we have those x successes times the probability that the rest are failures, n minus x. And there you go. So here you've got the combination equation that I was introducing in the first two slides. P and Q you have seen in the context of the geometric model, so I'm not going to belabor the point there. What are the mean and standard deviation of this guy? Well, the mean, you might be able to reason this through without anything remotely resembling a proof, and that's what I'm going to do for you anyway. That is equal to n times p. If these trials are independent, and we've got a probability of success of p for any specific trial, then n times p's got to be the number of successes I expect to see in those n trials. Standard deviation is easy, not intuitive, and I don't really want to derive it. I think I did that last year. I don't think we got as much value from that as I would have hoped. So that's the square root of n times p times q. Standard deviation of the binomial model. Okay, so everything between the squiggles. Important stuff. Again, expect if we've got a video quiz coming up to see this stuff on it. All right, B. Let's work on to B. Now that we've got the binomial model laid out for us, let's get some more play with it. What's the probability that I find at least 2 frogs of the 12 with this genetic trait? Okay, so we're going to combine the idea of the complement here with the binomial model. So the probability that, still using the same variable here, x, because success is defined the same way. Success is still seeing the genetic trait from the frog that we've pulled. The probability that x is greater than or equal to 2 is simply equal to... Now, the reason I don't want to attack that head on is because I would have to use the binomial model for 2 successes, 3 successes, 4 successes, 5 successes, etc., up to 12 successes. So let's think in terms of the complement here. If you want, you could draw yourself a Venn diagram to convince yourself that this makes sense. This is equal to 1, the size of the sample space, minus the probability that we have 1 or fewer trials, right? The opposite of 2 or more successes has got to be 1 or more successes. And those two things, this and this, add up to 100% of the sample space. So that's equal to 1 minus, I'll put brackets here, 12, choose 1. 12 frogs choosing 1 for success times the probability that 1 has a success, with the next 11 being failures. Or not next 11, that might be a little bit confusing, but some number, or 11 of them in no particular order being failures, plus 12 frogs choose 0 of them having success, which means no successes. P to the 0th is just 1 times q to the 12th for all the failures. And there you go. Not too bad. So that comes out to be, again, I don't want to belabor the mechanics here. I want you guys to see the stats behind this. So I'm not going to show you, that's 12 factorial over 1 factorial times 11 factorial, blah, blah, blah. That comes out to be 0.4533. And if you are worried about the mechanics, just trust that on the next day that I see you guys, I'll show you a calculator shortcut to make this a GIF. I don't know if that makes sense. To make this easy. Let's go with that. So there are A and B. All right, C, none of the 12 frogs has this trait. Well, that's not too bad. We've actually already computed that in the last example. That would be the probability. Still want to use X because success is defined the same way. Probability that X is equal to 0. Well, that is just 12, choose 0 frogs. We don't choose any of these frogs to be successes, times the probability of success to the 0th, because none of them have the trait, times q to the 12th, because all don't have the trait, equals 0.2014. Again, don't belabor the mechanics. Just find patterns in the logic here as best you can. D, so we've got C knocked out. D, no more than 4 frogs has this genetic trait. Okay. Well, a little bit of writing to do, but this isn't too bad. So we're talking about the probability that if no more than 4 frogs has the trait, then 0 might have the trait, or 1 might have the trait, or 2 might have the trait, or 3 might have the trait, or 4 have the trait. And there you go. So that's because, again, these are disjoint events. Cannot have only 0, only 1, only 2, only 3, or only 4 frogs with this genetic trait of a dozen, and any combination overlap. So that is just equal to 12 to 0, p to the 0th, q to the 12th, plus 12 choose 1. Oop, I don't want the parentheses. P to the 1st, q to the 11th, plus 12 choose 2, p to the 2nd, q to the 10th, plus 12 choose 3, p to the 3rd, q to the 9th, plus 12 choose 4, p to the 4th, q to the 8th. Okay, again, skipping the mechanics, we'll see more of that later. That's 0.9887, and there you go. There's binomial model. Nice extension from the geometric model. So let me summarize here real quick. I know we want to cut down on the length, and everyone wants to do that. I don't want to be up here a long time. You don't want to be listening to me a lot of time, or for very long in stats, because, well, a lot of people just don't enjoy stats. I'm okay to admit that. All right, so difference between the geometric model and the binomial model. Binomial model will find some number of successes in your end trials. Geometric model only ever works with a single success occurring at the very end. The geometric model is a simpler model. Binomial model has a lot more power to it. And sometimes it's hard to choose which model to use. You actually can, with any given, well, not with any given problem, but with some problems, you can choose either to use the geometric model or the binomial model, and either will make sense. Just make sure that the model aligns to the context. All right, last slide. This is cool, I think. You may not think that, and you're entitled to that opinion. Whatever. Slide 4 here. So we are told that suppose you take 50 independent school tests, each of which you believe you have a 1 in 5 chance of acing. With what probability do you expect to ace at least 15 of the tests? Okay. Well, ignore the histogram that we have here below, and relative frequency histogram, actually. And instead, for now, just focus on understanding the variable here. I think that's how I want to go about this. So we know that, again, sticking with x because I like to draw it, x is equal to the number of aced tests in 50 tests taken, where in this case n is equal to 50, p is equal to 0.20, right? So, I guess I should back up and say, yes, we could approximate this with the binomial model. We're not talking, we're not talking about only a success at the very end of our run of trials. We're talking about the successes being scattered throughout the 50 trials that we have. So that's the first thing you need to consider. Second thing is independence. We're told they're independent. By the way, I think I mentioned this with geometric models. Maybe I didn't, maybe I did. Either way, your book does kind of a lousy job of telling you when you should assume independence and when you should not. I think the motivation there is that they want you to think through realistically, could we assume the trials to be independent and not affect each other, or is that not a fair assumption? I understand the logic there, but on the AP exam, you better believe that if you've got a series of trials that you are talking about, that they're describing to you and that they want you to use to solve a problem, they will tell you if you have independence. So for now, the book is trying to encourage realistic thought. The AP exam does more of a test-taking approach and just tells you if you've got independence, so you know whether or not it's appropriate to use a particular model. Okay, anyway, we want to know, with our geometric model, everything's set up here, we want to know the probability that x, the number of tests aced, is greater than or equal to 25, which is equal to the probability that x equals 25 union with, or x equaling 26, unioning with, all the way up the line, x equaling 49, unioning with x equaling 50, which equals this. That is a nightmare. You do not want to solve that directly. So you're talking about 26 applications of the binomial model, each of which is already involved enough to multiply out, even with calculator shortcuts. That is not how we want to go about this. Instead, the reason I presented this histogram to you of the probability that you would have, in successes in 50 independent tests being taken, is that I want you to see basically just the shape of this graph. You can see very clearly here that the shape of this histogram is very much the shape of a normal model. And that's going to be our saving grace on this problem. We can, as long as, I should really write this out so that you all get it, as long as you expect at least 10 successes and 10 failures in trials, you can approximate, you can approximate the binomial model with the normal model. That is awesome, because what we're going to do, we're going to use our trusty old z-score here and make it happen. Okay, so first of all, there is embedded in that summary that I just gave you, you've got two conditions that you need to make sure are met for any particular problem to which the binomial model also already applies. That's confusing. Okay, let me back up. We know the binomial model applies to this problem because we have Bernoulli trials. These are independent results. There's only success or failure, only acing or not acing these tests that we care about. Okay, so that's been taken care of. The binomial model would work. Now, at least 10 successes and 10 failures. Well, come back up here. We know the binomial model would work. How do I find that, that I should expect at least 10 successes? Well, that is just the expected value of x, where x follows a binomial model. That's the mean of the binomial model, which I just gave to you as being n times p. So 50 tests being taken times the probability of success of 0.20, that's 10 that we expect to pass. So that condition is met. Hurrah! The second thing you have to check is n times q, the expected number of failures, also greater than or equal to 10. Well, obviously it is. It's got to be 40. But showing you the math, it's 50 times 0.80, which is 40. So that condition's also met. So, okay, what I'm going to do is circle this guy. We need that. If we're going to approximate the binomial model with the normal model, we need to know the mean of the binomial model, because that's going to be the mean of the normal model we're going to approximate the binomial model with. So we got that. We also need the standard deviation of x, which is equal to We said NPQ, all under a radical last slide. So 50 trials, 50 tests, times probability of success on any one is 0.20, times probability of failure is 0.80. That comes out to be 2.83. Circle that, also important. So, up here we do not have a normal model. Don't use that histogram as a normal model. Let's go ahead and draw the approximation to the binomial model as a normal model. So, I am the king of leaving myself no room for a title. The number of tests aced in 50 is what this normal distribution is of. So, okay, we said that the mean of the binomial model here is 10. We expect to pass 10 of them. Standard deviation of 2.83. So one standard deviation out to either side, you are at 12.83. Oh, that's an 8. Or 7.17. And we want to know the likelihood that we would pass at least 15 of them. So we need the z-score. Hooray! We need to know how many standard deviations from the mean is 15 tests being aced. So 15 is the data value we care about. Subtract off the mean here of 10. Divide through by your standard deviation of 2.83. You'll find a z-score of 1.77. Awesome. So, wrapping this up, we are almost finished. Hopefully this is a shorter presentation than you've seen thus far. The probability that x is greater than or equal to 15 is equal to the probability, and Jacob asked a really good question about this last time. What's this jump between the first thing you have right here and the thing that's going to follow? Z being greater than or equal to 1.77. Okay, now we've talked about this before, but it's been a long time, so I think it's only fair that you would forget. If we want to know the probability that you would have 15 or more successes, 15 or more aces of these 50 tests, you can alternatively think of that number 15 in terms of the number of standard deviations away from it that it is from the mean, and you're still talking about the same data value, right? If we've got a distribution that has a mean of 10, standard deviation of 2.83, then if I talk about data value 15, or I talk about z-score positive 1.77, I'm talking about the same value on the distribution. It could be z equals 1.77, or I didn't leave myself any room, but at the bottom what I would put is 15. They mean the same thing. It's just two different ways to refer to the same thing. Just like scientific notation is the same as writing a number in standard notation, just two different ways to refer to the same thing. But we use the z-score because your calculator has access to all these tables that it can use to compute particular probabilities. That's why we go from this to this. That's why we go from the data value of interest to the z-score, because your calculator can work with z-scores in a kind of a universal global context. It can't work with data values in that same way. All right, so probability that z is greater than or equal to 1.77, just use normal CDF. 1.77 up to 1,000, which is equal to 0.0384. And you guys are done with the notes. That is it. So you've seen the combination equation. Whoop. You have seen the binomial model, and you've seen the normal approximation to the binomial model when numbers get big, provided this condition that's in the middle of your screen in red is met. Have a great weekend, guys.